The simple pendulum. Simple harmonic oscillator, SHO, are systems that oscillate with simple harmonic motion. There are common types of simple harmonic oscillators. Simple harmonic motion, SHM. We know what simple harmonic motion is. When an object is at equilibrium here, and you displace it, and then you release it, the object will go back to equilibrium and overshoot. And then they keep going back and forth. As they go back and forth, that's what we call simple harmonic motion. Here's a simple pendulum. Pendulum that is displaced by a distance of x. So it's displaced by a distance of x from there to there. This pendulum, when pulled, would want to go back to the equilibrium. Because it wants to go back to equilibrium, that's called restoring force. It's the force that wants to pull it back to equilibrium. So you got the pulling force and you got the restoring force. The displacement is going in the positive direction here, but the restoring force is going back in the negative direction. So what we tend to do is draw the pulling force here. So that's the force pulling the mass. This pendulum mass is actually called pendulum bob. So that's pendulum bob. But as you pull it to the right and have a displacement of x, it will want to come back to its equilibrium here. So the line of equilibrium is basically this line here. So that's the line of equilibrium. Now the weight of the force is acting downward, and that's mg. And that weight is acting parallel to the line of equilibrium. Now we can extend that line so that we can create an angle theta subtended by the arc length x. So if I extend the line, and then I could draw it perpendicular to that tangent line here, and that perpendicular will be parallel to the pulling force. Here's the pulling force, it's a tangential. That's the restoring force, trying to restore it back to the equilibrium. And this is the pulling force in the opposite direction. I'm going to draw a perpendicular now to the tangent line, which is parallel to the restoring force. You can see that's a right angle triangle. And the vector diagram is that line is coming down that way and it's going that way. So obviously the line of weight acting in that direction will meet that line to form a right angle triangle. So if I extend that, I can get a nice right angle triangle. Now you can see that this angle here will be correspondingly equal to this angle here. So this angle here is also theta, because it's corresponding angle. This line is parallel to that line and they both cut that line. So that angle is corresponding to that angle. Now I could find the value here for the force that is pulling, the restoring, because this force, this line is parallel to that. So the value of this force is equal to that restoring force. Let's call that y. If I use SOHCAHTOA, and I'm using the first three, that would be sine of an angle. Sine of an angle theta is opposite as opposite over hypotenuse. That's the opposite to the angle, right opposite. and that's the hypotenuse. So that would be y over mg. So what I can do is multiply both sides by mg, or just cross multiply. Don't forget that's over 1. So if I cross multiply, then that will give that will make sine mg sine theta equals y. So now I know that Fr, the restoring force, is mg minus mg sine theta, because it is going in opposite direction to the displacement. So now I can say Fr is equal to minus mg sine theta. But the pulling force, applying Newton's second law of motion for the pulling force, so we got, let's just say we got pulling force, which is Fp, and we got the restoring force. Now I know that the restoring force and the pulling force will be equal. So I could say Fp, the pulling force, is equal to the Fr. But my Fp, using Newton's second law of motion, will be ma, because I'm accelerating the mass as I pull it. But A wants to go back to equilibrium, hence that will become the minus mg sine theta. As you can see, m will cancel m, a will be equal to minus g sine theta. When theta is small, so for a small angle of theta, so sine of theta is approximately equals to theta, where theta is less than 10 degrees. So where theta is less than 10 degrees. Now I could rewrite my equation as A, acceleration, equals minus g theta. But what is theta? Theta is that angle here created by the arc length and the length of the pendulum, which is the radius, because it could form a circular motion. So that, let's write what theta is then. X over theta equals L. X over theta equals L from the arc length, the sector here. And therefore, we could write theta equals X over L. Now that we know theta is X over L, we know that A equals minus g theta. Therefore, A equals minus g x over L. The acceleration for simple harmonic motion is A equals minus omega squared x. This is the x we're talking about. And so I can replace A here with that, and therefore we get minus omega squared x equals minus g x over L. Now you can see the minus, we cancel minus, x, we cancel x, and therefore I get omega squared equals g over L. Because I'm also experiencing simple harmonic motion, I also know that the omega here is, omega can be written as 2 pi f, where f is the frequency, or omega can be written as 2 pi over t, where t is the period. So we can say f equals frequency and t equals period. So what we can do now is now write a relationship between frequency and period, and the relationship is frequency equals 1 over period, or period equals 1 over frequency. So we're going to apply that here with this equation that we just got. So we now know that omega squared equals G over L. If I square root both sides, I get omega equals plus or minus root G over L. But I can now replace my omega with 2 pi f, or 2 pi over t, and I get 2 pi f equals plus or minus root G over L, where f will be, I divide both sides by 2 pi, 1 over 2 pi root G over L. I can only have positive frequency, not negative frequency. So that's the first frequency equation. Then I can write period equation as well, because period is 1 over frequency. So, or I can just replace period here. I can use 2 pi t here, and to find the period will be equal to 2 pi root L over G. So it's a reciprocal of that. Reciprocal of 1 over 2 pi is 2 pi, and reciprocal of root G over L is root L over G. So that's the period equation for simple harmonic motion. That's the period equation for the simple pendulum. And that's the frequency equation for the simple pendulum. So what I can do is, let's start with frequency. So the frequency is basically root G over 2 pi times 1 over root L. It's the same equation. As you know, in surds, you could write root G over L to be root G over root L. So I'm just using that, and I've just separated that here. So that's G, by the way. So now this relationship now looks like Y equals mx. So I'm plotting a graph of Y equals mx. You can see to plot a graph of Y equals mx, I will be plotting frequency in the y-axis, and I'll be plotting 1 over root L in the x-axis, and my gradient is going to be root G over 2 pi. So what that entails is that you draw a graph and plot frequency against 1 over root L, whereby you're changing the length here. So that graph could give me a straight line graph through the origin, and if I find the gradient, I need to pick 2 points, and that would just draw that down to find the gradient, and that gradient is equal to root G over 2 pi. But at the same time, I could square both sides in order to get rid of the square root. So if I square both sides of the frequency, and then I could get f squared equals 1. Well, put it this way, if I square both sides, I get f squared equals G over 4 pi squared times 1 over L. So again, if I plot a graph of, instead of 1 over root L. I'll plot the graph of 1 over L, as you can see here, and I'll plot frequency squared, my gradient. So here you go. So that's y equals mx. So my gradient will be, or the gradient will be g over 4 pi squared. And I'm plotting 1 over L against, plotting f squared against 1 over L. So the gradient is going to be g over 4 pi squared. You could do the same with the period as well. We could plot, we could rewrite that equation. We could say t equals 2 pi over root g times root L. As you can see, again, plotting t against root L, the gradient will be 2 pi over root g. Or you might want to square both sides, where you will get t squared equals 4 pi over g, 4 pi squared over g times L. And again, if you plot the y against mx, as you can see, the gradient, you're plotting L against x and t squared in the y. So you're plotting t squared against L, and your gradient will be 4 pi squared over g. So with this simple pendulum, so when you plot the t squared or t against L, so if you plot t squared, as you can see, against L, t squared obviously in second squared and meter. As you know, the graph goes through the origin. And just to remind you, you pick 2 points on the graph, you find your gradient, and that gradient, we said, is, that gradient for that is 4 pi squared over g. So what we're saying is t squared is directly proportional to L, or t is directly proportional to root L. So if you want to get a straight line with this, you have to plot t against root L, and that will be your gradient. Now, if you're plotting the graph against mass, because the equation here does not depend on mass, it only depends on g and L, and g is constant on Earth, so you can only vary the length. If you were to plot t squared or t, or just t against mass, your mass is not dependent on t, therefore you're going to get a constant line. So if you plot, let's just draw that one. If you plot t against the mass in kilogram, so your graph will be a straight line like that. And if you plot the amplitude as well, because this is an oscillator, because it goes oscillator here, the amplitude is A for the oscillation, and you can see there's no amplitude in this equation. Again, you're going to get, if you plot t against amplitude, which is in meters, the maximum displacement, you would find that it's a constant graph as well. So don't forget t is in seconds, and that's seconds. It will be a constant graph. If you plot t against mass in kilogram, you're going to get a constant graph because it doesn't depend on t from the equation. And if you plot A, the amplitude is in maximum displacement, and you're going to get a constant graph as well. So let's just say A equals amplitude. M equals mass. So if you plot If you plot T against M, you're going to get constant line. And if you got T against A, the amplitude, you get constant line, because they're not in the equation.